We talked about X-ray crystallography, which is one of the main techniques that we use to figure out what the crystalline lattice is of a solid. And so now we're going to look at what sorts of different crystalline lattices are possible. By crystalline lattice, we mean the arrangement of atoms within a crystalline solid. These are regular. They're going to have repeating patterns in 3 dimensions. Which particular type of crystalline lattice happens in a given solid depends on the energy level. They are going to arrange themselves so that they will have the lowest energy. When we look at these lattices, we're going to look at the unit cell. I think there's actually something wrong with this phrase here, the smallest divisible unit. I think it's supposed to be indivisible, maybe. It's the smallest unit of a crystal that, when repeated in 3 dimensions, reproduces the entire crystal. So I think maybe if we just got rid of that word, that might be better. So here we have a 2-dimensional representation. The circles here, the circus. Let's go to the circus. The circles are the lattice points, and those represent where the center of the atom or ion or molecule is. The dark red square here, going from the centers of these lattice points, that is the unit cell for this particular arrangement of circles. If we take this square and we repeat it over here, and we repeat it down here, and we repeat it over and over and over again, we will get this overall structure. That is the smallest piece that you can do that with. You could, of course, take larger pieces. You could take this whole square here, and you could repeat that in 3 dimensions, but we want the smallest one, okay? So that's what we mean by a unit cell. We are mostly going to be looking at cubic unit cells, but there are a lot of other types of unit cells as well. Cubic unit cells have equal edge lengths and 90-degree angles. That's the definition of a cube, right? So here we have a cube. All the length, the width, and the height are all the same, and all the angles are 0. 90 degrees. We can change the angles, the lengths of the sides, and come up with all these different types of shapes. And all of those are present in various crystalline solids. We're, for the most part, just going to be looking at the cubic ones, but the others are there. We're going to look at unit cells where all of the atoms are identical. We're going to use some different colors, but that doesn't mean that those are different atoms. It's just to help us to be able to see more clearly. So a couple of quantifications that we have about these. Coordination number, that's the number of atoms that each atom is in direct contact with. How many atoms are they touching? That's important because the atoms that are in contact, in direct contact, are going to have the strongest interaction. Packing efficiency is the percentage of the volume of the cell that's actually occupied by the spheres, ions, molecules, whatever. If we have a higher coordination number, we have a greater packing efficiency. High packing efficiency means there's less empty space. So here are the 3 main cubic cells that we're going to look at, and we'll look at these in detail, but this is sort of a summary. There's a simple cubic, a body-centered cubic, and a face-centered cubic cell. And this compares coordination numbers, gives the equation for the edge length, gives the packing efficiency, and the number of atoms in a unit cell. I don't expect you to memorize this stuff. You should become familiar with what we mean by simple cubic, body-centered cubic, or face-centered, especially coordination number, edge length, packing efficiency. Those sorts of things would be given to you on an exam if you need them. So we'll start with the simple one, simple cubic unit cell. So here we have one atom at each corner of a cube. A cube has 8 points, right? 8 corners. And at each of these corners is 1/8 of an atom. So we have 1, 2, 3, 4, 5, 6, 7, 8 atoms, but there's only 1/8 of each of them. So this cell contains 1 atom. It's 1/8 of 8 atoms. If you took all these pieces and put them together, you could make 1 atom. On the sides here, if we say that r is the radius of the atom, then the length of the side is 2 times that radius because they touch along the edge. So L, the length of the side, is 2r. Some different views of this. This is the picture we just looked at. If we look at the whole atoms that are part of this cubic unit cell, we see that what we've got here is atoms stacked on top of each other and right next to each other. Then if we look over here, this is where we can see the coordination number. Looking at this atom here in the corner, the coordination number is how many atoms are directly touching that atom. Well, it's touching this one, and the one on that side. Those are all within this cubic unit cell. And then it's touching 3 that are in neighboring cells. So 1 atom is in contact with 6 other atoms. So the coordination number is 6. We'll calculate packing efficiency in a minute, but for now I'm just going to tell you the packing efficiency here is 52%. So you pack all these spheres together and 48% of it's empty space. You can play around with different unit cells by taking marbles or other similar sized spheres, oranges or apples or something, and see how you can pack them together in a box. So here we're going to look at packing efficiency in a 2-dimensional lattice. So this is asking us to calculate the packing efficiency of the 2-dimensional lattice shown here. And here we have in the white square, that is our unit cell. I'm going to abbreviate packing efficiency as PE. So packing efficiency is the normally the volume, but here this is 2-dimensional, so we're looking at areas instead. It's the area occupied by the atoms divided by the area of the unit cell. And it's a percentage, so we multiply by 100. There are no numbers given here. We have no idea what size these circles are, but that's okay. So what we're going to do is we're going to say that R is the radius of a circle, or the radius of one of these atoms. So in this white square, if we put these pieces together, how many atoms or circles are in that square? 1, right? Because here's a fourth of a circle, and here's a fourth, and a fourth, and a fourth, and there's 4 of those. So there's 1 atom in the unit cell. So there's 1 atom, can't spell, 1 atom in that unit cell. What is the area of that 1 atom? What's the area of a circle? Pi r squared? Area equals pi r squared. So we've got 1 atom in there, and its area is pi r squared. So we could plug that into our equation up here. Pi r squared. That's the area occupied by the atoms. What's the area of the white box? How long is an edge? This is R. And this is R. So the edge length is 2R, right? The area of a square is the length times the width. So the area of the cell is equal to 2R squared. And we could simplify that and say, well, that's 4R squared. You following? So the area of the actual unit cell is 4R squared multiplied by 100. And the R squareds cancel out, don't they? Which is convenient because we don't know what they are. So we've got pi divided by 4. Use your pi button. Don't abbreviate it as 3.14. So pi divided by 4 times 100. 78.5%. That's the packing efficiency, two-dimensional, for that lattice. Any questions? The next unit cell is the body-centered cubic unit cell. So here we have this gold sphere in the middle here, representing an atom. That is the same kind of atom as the purple ones. We're using a different color just so we can see it more easily. Because if it was all purple, it'd be hard to see what was going on. So in this cell, we have a sphere, an atom in the center, and we have those atoms at each corner. So now the atoms do not touch along the edge. So the length of the edge is no longer 2R. It's longer than that. So to calculate it, we have to look at some dimension of this cube where the atoms do touch. And they're going to touch from this corner through the center up diagonally to the other corner. That distance is R, and here's R again, and R, that's 4R. And what we're trying to find is this L here, and so you can use some geometry with triangles, and you come out with L is equal to 4R over the cube, or the square root of 3. And again, you don't have to memorize that. But you need to know what it represents. So if we have one atom in the middle and these at the corners, what's the total number of atoms in that unit cell? 2, right? Because each of these is still an eighth of an atom, so altogether those add up to 1 atom, plus this whole atom in the middle. So this unit cell contains 2 atoms. So it's 2 atoms. We've got 1/8 times 8 plus that 1 in the middle. If we show the purple atoms whole, we get this representation. And then we extend that, looking at this purple one in the corner and seeing how many atoms does it touch directly. Well, it does not touch the other purple atoms, does it? It only touches the gold ones directly. But it's going to touch 8 of those. So the coordination number is 8, and the packing efficiency has gone up at 68%. There's less empty space in this unit cell. So we could do problems like this. An atom has a radius of 138 picometers and crystallizes in the body-centered cubic unit cell. What is the volume of the unit cell in cubic centimeters? Well, to do this problem, we need the equation describing the length of an edge. L equals 4r over the square root of 3. So we're told that the atom has a radius of 138 picometers. So r is the radius of the atom. This is the length of the edge. It's a cube. As we've got a cube here. This is L, and that's L, and that's L. And so the volume of the cube is the length times the width times the height, or L cubed. So that was L. The volume then is L cubed, which equals that, 4r over the square root of 3, raised to the third power. We know what r is. We can plug it in here and calculate the volume. What unit would that give us, though? Cubic picometers, right? And it says we need to do it in cubic centimeters. I think it's easier to convert this to centimeters first before I cube it. Okay, so that's what I'm going to do. We're going from picometers to centimeters. Both of those units have a prefix, so we should do this in 2 steps. So first we're going to go to meters and put picometers down there. And then we're going to go to centimeters and put meters down there. Centi means 10 to the minus 2. So put 10 to the minus 2 here. 1 centimeter is 1 times 10 to the minus 2 meters. Pico means 10 to the what? It's not 9, because that's nano. They're multiples of 3 for the most part. Nano is 10 to the minus 9. This is the next one. It's 10 to the minus 12. So 1 picometer is 1 times 10 to the minus 12 meters. So 138 times 1 EE negative 12 divided by 1 EE negative 2 gives me 1.38 times 10 to the minus 8 centimeters. So I can put that into my equation. 4 times 1.38 times 10 to the minus 8 centimeters divided by the square root of 3, and that whole thing raised to the third power. I'm going to do 4 times 1.38 EE minus 8, and I'm going to divide by the square root of 3, find out what that is, 3.187 times 10 to the minus 8, and then I'm going to raise that to the third power, and I'm going to get 3.24 times 10 to the minus 23rd. Cubic centimeters. Any questions? Should the volume of that cell be really, really small? Yeah, it should. Because how many atoms are in that body-centered cubic unit cell? 2. And so there's some empty space around them, but it's still going to be really small. Any questions? Then we have the face-centered cubic unit cell. So here we have an atom centered on each of the 6 faces, plus the ones at the corners. So this is half of an atom, and that's half of an atom. There's 6 of those, so that's 3 atoms plus the one spread around the corners, so that we've got 4. Here the atoms are touching along a diagonal face. In body-centered cubic, they touch diagonally from one corner of the cube to the other. Here it's just along the face. And so this This line here would represent 4R, and so from that we can calculate what L is. L is 2 times the square root of 2 times the radius. Here we've got that again, showing how it's 4 atoms. This is showing complete atoms all around, and you see how that's a bit hard to look at now, right? It's hard to see exactly what's going on in there. And then here, looking at the packing efficiency, we're looking at this atom in the corner, and it is in direct contact only with gold atoms, and so if you dig your way through that, you'll find out the coordination number is 12. We can calculate the packing efficiency at 74. So it went from 52 to 68 to 74. As the coordination number increases, the packing efficiency increases. Any questions? Chromium crystallizes with a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeter. So what kind of a unit cell is this? It's body-centered. We just talked about face-centered, and so it's tempting to just automatically assume that it's face-centered. It's body-centered. So we're going to use the equation for the edge length for the body-centered, which was 4R over the square root of 3. So we've done a calculation where we calculated the volume of a unit cell, right? So the volume would equal that cubed. But this time it's asking us for the density. What's the equation for density? Mass divided by volume. Well, here's a volume. That's the volume of 1 cubic unit cell. Could we find the mass of 1 cubic unit cell? What does the periodic table tell us? Gives us the mass in grams of a mole of atoms, right? How many atoms are in the body-centered cubic unit cell? 2. 1 in the middle, the body-centered one, and the corners that add up to 1. So here we have 2 atoms. We need to find the mass of 2 chromium atoms. So let's think about a path here. We've got atoms, and we want to get to grams. We've got the molar mass. That relates moles and grams, right? So if we had moles in the middle here, we could get to grams. Do we know the relationship between atoms and moles? Avogadro's number, right? So we'll go from atoms to moles to grams. So atoms and moles, 1 mole is Avogadro's number of atoms. And the molar mass we get off the periodic table, 51.9961 grams for 1 mole of chromium. Two divided by 6.022 EE23 times 51.9961. It's a very small number because it's the mass of 2 atoms. So 1.72687 times 10 to the minus 22 grams. So we can plug that into our density equation as the mass. That's the mass of the unit cell. And now we need to find the area in cubic centimeters. So we did one like this already. I'll show you a little bit of a different way to convert that picometers. So we have 125 picometers, and I want to get to centimeters. I could convert this to meters very quickly by just writing what pico means instead of the p. So if I erase this, and instead of pico, I write times 10 to the minus 12, because that's what the pico represents, meters. And then I can convert this to centimeters. Centimeters up here, meters down there. 1 centimeter is 10 to the minus 2 meters. And so we end up with 1.25 times 10 to the minus 8th centimeters. As the radius of a chromium atom in centimeters. So then we plug that into this area equation. So I've got 4 times 1.25 EE minus 8 divided by the square root of 3, and that whole thing raised to the 3rd power, 2.4056 times 10 to the minus 23rd cubic centimeters. Yes, I forgot to write that. There we go. I've got it over here. Yeah, I cubed it. I just forgot to write that down. So that's our volume. There it is, 1.72 divided by the 2.4. Oops, I did something wrong. Let's try that again, 1.72687. Having issues today. Divided by 2.4056, E minus 23. There we go. Coming up with 7.18. grams per cubic centimeter. Is that a reasonable density for a metal? What's the density of water? 1 gram per cubic centimeter, or 1 gram per million. Are metals more dense or less dense than water? More dense. Hey Siri, what's the density of chromium?
The density of chromium is about 7.14 grams per cubic centimeter.
Pretty close. 7.14 versus our calculation of 7.18. Any questions?
So the relationship between volume and L, take B for everything, just V equals L cubed?
V equals L cubed for these cubic unit cells.
Yeah,
Not for any of the others, but for the cubic unit cells.
Okay.
And then you need to know what L is in terms of something measurable. So if you know how the atoms crystallize, what unit cell they have, you could measure the density and you could figure out the radius of the atoms. Yeah. Another way to look at these crystal structures is to think about stacking the atoms in layers. So you can imagine taking a box and putting oranges in the box, right? You arrange one layer and then you put the next layer on top. And there's different ways that you can pack them in. There's one way that they're going to want to go in, but there are other ways that you can make them stack. So a simple cubic structure, that first unit cell we looked at, is where we have layers of atoms where the atoms are in rows and columns and they're stacked right on top of each other. It's hard to get spheres to stack like this when you don't have intermolecular attractions to pull them together. There's a lot of empty space in this packing structure.
It's better to pack like
Yeah, this will be a lot more efficient. Here we have this row is a little offset from that row, and so these can get closer together. Let's see if I can sort of replicate that. Oh, that's still too small. So that's my representation. This would be the simple unit. So they're in rows and columns. And there's going to be more empty space there than when you offset the rows a little bit, because now they can get closer together.
So if they're structuring to get to the lowest level of energy, why wouldn't they all pack in?
That's an excellent question. Why don't they all go to the closest pack? We'll get to that. It's an excellent question. So this is more efficient in the single layer. And so these structures that use layers like this are called closest packed structures. So here's our first level in the red. And then the second one, we have a choice of how we line this up. It's more efficient if we stagger this as well. So this blue ball is sitting in the little divot here caused by the 3 balls down here, instead of trying to balance directly on top of one of the red balls. So this is making this staggered pattern, but in the other dimension. Does that make sense? So these are going to nestle closer together. So we've got layer A and layer B, and then we also have a choice when we stick the third layer on. So both of these are closest packed structures, but one is an AB-AB pattern and the other is an ABC pattern. So here we have layer A, layer B, and then layer A again. So here this red one is exactly above the one on the first level. So these line up exactly, and then these are in between staggered. So this is an AB-AB pattern. This unit cell is actually not a cubic unit cell, it's a hexagonal unit cell. And so this is called hexagonal closest-packing. So this would be the unit cell, this guy right here. And it's not cubic because the angles are not 90 degrees. They are, we've got 60 and 120. And when you put a couple of these together, you can see the hexagon, and that's why it's called hexagonal. If we take the third layer and offset that from the first layer, so the third layer is offset from the first layer and the second layer, we now have what's called a cubic closest pack. So ABC pattern, And this is identical to the face-centered cubic unit cell. So this is the different layers stacking up that we were looking at. Here's the first layer. The second layer is offset. The third layer is offset from both of them. The fourth layer then would repeat and would line up exactly. Put those together and tip it on its side, and here we have the face-centered cubic unit cell. This red one is on the face, the blue one's on the face, that red one's on the face, and if you cut off the excess, you get this. It's a face-centered cubic cell. And we saw that that face-centered one had the highest packing efficiency. Yeah. So, like in Reedley, where packing fruit is a big business, you pack your fruit so that you can get the most fruit in the box, right? Because it doesn't take up as much space in the truck. It's more efficient.